Okay, we're going to try to solve here parts A and B of number 49 in chapter 2 in your book. Let's just read it quickly. A 200 kilogram weather rocket is launched with 100 kilograms of fuel and fired straight up. It accelerates upward at 30 meters per second squared for 30 seconds, then runs out of fuel. Ignore any air resistance. And then they ask us a couple things. What is the rocket's maximum altitude? What's the highest point that it reached? How long is the rocket in the air before hitting the ground? And then they want us to draw a velocity versus time graph for the rocket from liftoff until it hits the ground. We're going to focus on parts A and B here. So let's just get started. And again, making sure that we're just following a procedure and being very organized, because there's a lot of stuff to keep track of. So let's just see if we can visualize this. What are we looking at? So basically what we have is we have a rocket. And we're going to say that rocket starts at 0. And they tell us it travels for 30 seconds. Travels up here for 30 seconds. Time equals 30 seconds. And its acceleration during that is 30 meters per second squared. And at that point in time, it runs out of fuel. So it's no longer accelerating due to the rocket engine. It runs out of fuel. At that point, actually, it's in free fall. So we're going to then look at the different phases of its travel. So at that point where it runs out of fuel, okay, we'll just draw the rocket. What does it do? Well, the rocket up at that point the rocket continues to move upwards, but now it's slowing down until it reaches a maximum height. We'll call it Y max. It's going to go up to some maximum height, of which time it will stop moving upward. And for an instant in time, its velocity will be equal to 0. So at that point in time, then it's going to turn around and start falling back. So let's just call this first part phase 1, while the rocket is firing. Phase 2 is the engine's died, but it's still rising, it's still going up. Phase 2. And then the last one, we'll assume that, I don't know that the rocket flips around, but let's say the rocket flipped back around. And so, doesn't necessarily do this, but we'll draw it that way. So at that point in time, now the rocket is coming back down. Okay? And it's going to come all the way back down here, back to the ground, which we listed at 0. And that's phase 3. Okay? So as we look at that, let's just fill some other things in as we look at it. Well, we're going to set up as being positive in the y direction. So we set that. We already determined where 0 was. We're going to call that at the ground. We know our time is 30 seconds in the first place. We know the acceleration. We know our initial velocity equals 0. Final velocity of 1, but we also know whatever my final velocity is, the instant time that that rocket engine stops, whatever the velocity at that point is, becomes the initial velocity for phase 2. And we also know up at this highest point, my final velocity in phase 2 is equal to 0. At that instant in time, it's equal to 0. And we can come over here, and I'm sorry, during phase 2, well, its acceleration is due to gravity, minus 9.8 meters per second squared. As it is in phase 3, acceleration is minus 9.8 meters per second squared. Because at those points, at both of those points, it's subjected to free fall. It's just the effect of gravity. That acceleration due to gravity. Well, we also know over here at phase 3 that the final velocity at 2 is going to be my initial velocity at 3, and we know that those are 0. We know that those are 0. And now we can go ahead and we can start looking at some things. So take a minute, just take a minute or two to take a look at this. I'm going to go ahead and just shrink it a little bit so we can try to get everything here on one page. So I'm going to just pull that down a bit there. While you look at it. What did they ask us to find? Well, they asked us to find A, they wanted to know, I believe, the maximum height or the maximum altitude. So we'll just call that Y max. And B, what did they want? Well, B, they want to know how long is the rocket in the air before hitting the ground. So they want to know time total. So we're going to need to find some things out about each one of these phases. On each one of those, we're going to need to determine a few things. So, not sure what that's doing there. Okay. So first thing we want to do, let's look at phase 1. And we need to find out, well, we got to find its maximum altitude. We got to find out first how high is it at the end of phase 1, and then we'll find out how much higher did it go up in phase 2. So we can certainly look at that, okay? So let's just take a look at that real quickly. But let's ask ourselves, let's make sure that we're following a consistent procedure. Ask ourselves in phase 1. First thing we want to do is determine what kind of motion is it. And we just ask, does it have an acceleration, yes or no? Well, yes, it does. And is that acceleration constant, yes or no? Well, they gave us a singular value, 30 meters per second squared, so it is. So again, we come back to when we have constant acceleration, we have those equations that we can use to solve that particular special case. So we have these constant acceleration equations that we can certainly use to solve this. So let's look first off here, let's look at phase 1. Phase 1, let's do the same thing we've done so far. What do we know? Well, Y initial, Y final, V initial, V final, acceleration, and time. Let's go ask, and these are all during phase 1. So we can go in and just fill some of these in. Well, my initial position is 0 meters. My final, I don't know. I'm looking for that final position. My initial velocity is 0. My final velocity, I don't know yet. My acceleration is 30 meters per second squared. And the time is 30 seconds. So let's just see if we can find that final position. Well, the final position as we look at that, sure enough, we can find this from this middle equation here. We know that our final position equals our initial position, which is 0, plus our initial velocity times time. Well, initial velocity is 0, so that's 0, plus 1/2 AT squared. So that basically becomes this. Y final is Y initial plus V initial times time plus 1/2 AT squared. And when we go through this, well, this is 0, and this term is 0. We basically have Y final equals 1/2 AT squared. And when we plug into this, we get 1/2 30 meters per second squared times 30 seconds squared. And when we do this, I believe we get 13,500 meters. You get 13,500 meters when we do that. So that's where we're at. Shrink this up just a little bit. So that's, now we know Y final there, but we also need to know my final velocity in 1, which is just my initial velocity plus acceleration times time. If we plug in here, we're going to get 0 plus 30 meters per second squared times 30 seconds, which is 900 meters per second. So now we know some information as we go in to phase 2. Okay? So now we're going to go into phase 2. So let's just put a line here and let's take a look at phase 2. And let's do the exact same thing that we did before. We're just going to be repeating that. So for phase 2, we have Y initial equals into Y final of 2 equals V initial for 2 equals V final for 2 equals acceleration and time. So let's just plot those in. Well, we do know my initial velocity in 2, remember, is my final velocity for 1. So my initial velocity is 900 meters per second. And I'm sorry, I was putting that in the wrong place there. We do know my initial position, sorry, is 13,500. I mixed that up there, meters. My final position, I don't know. My initial velocity now is the final velocity in 2, 900 meters per second. My final velocity is that point where it's at its highest point. My final velocity is 0. My acceleration is gravity, minus 9.8 meters per second squared. And time, I don't know. But we'll need to find that, I just don't know it yet, okay? But we'll get it, just don't know it yet. Let's kind of position that over there so we can keep going. So again, what do we want to find out? Well, let's find out how high does it travel up, or just see what we can get. Well, again, its maximum height, Y final equals Y initial. We know Y initial. We don't know time, so that becomes a quadratic equation. Yeah, probably don't want to mess with that as much. Well, we don't know time, so let's find, we do know V final, we do know V initial, we do know acceleration. Let's use that last equation. And let's solve for that maximum height. So we know V final squared equals V initial squared plus 2a, my change in position, We know that. So V final is 0, but let's just solve this for delta y. Well, if you solve that for delta y, you're going to get V final squared minus V initial squared all over 2 times A. And if we plug into that delta y, V final is 0 minus V initial, which was 900 meters per second squared, all divided by 2 times a minus 9.8 meters per second squared. Well, as we look at this, we also know that delta y is y final minus y initial. So if we just do this real quickly, what you would have really is y final equals y initial, which is 13,500 meters, all of that plus, really what we get is minus 900 meters per second squared divided by 2 times a minus 9.8 meters per second squared. And when we do that, we're going to get y final equals 54,800 meters. So there we go, 54,800 meters finally. Well, let's just see if we can shrink this up a bit. Let's just see. Grab a little. Okay, let's just shrink all of this up. Move it down here a little bit. I know that got a little light, but move that down there. Now let's go to phase 3. And we're going to do the exact same things for phase 3. Now, I did leave out in phase 2, now that we know that final position, in phase 2, we really should come back and, find time. And in phase 2, we can find time. I'm sorry to jump back there for just a second, but we can find time from the equation V final equals V initial plus acceleration times time. And if we solve this for time, we're going to get time is equal to V final minus V initial, all divided by the acceleration. And if you plug into that, we're going to be able to get time there. So plug into that real quickly. And when we do that for our second phase, that comes out to be about 122 seconds. So sorry to step back there real quickly. So now let's go back to phase 3. Phase 3, we have y initial for 3 equals y final for 3 equals v initial for 3, v final for 3, acceleration, and time. And again, let's step through each one of these and just see. Well, my y initial for 3 is just my maximum height, so I'm at 54,000, whatever we were, 54,800 meters, so I'm a ways up there. Okay. My final position, well, I'm back at the ground, I'm at 0 meters. My initial velocity at 3 was my final velocity at 2, which we determined to be 0. My final velocity, I don't know. My acceleration, minus 9.8 meters per second squared. And my time, I don't know. I'm looking for the time. That's something that I would like to find out, or need to find out. So now if we look at this, and again, you know, if we ask the question, does it have an acceleration, yes or no? Yes, it does. Is it a constant acceleration? Yes. Given that all being true, then we can look at our equations up here. Well, let's take a look. What I really want to find, I found my maximum height. I want to find time. Time to fall back to the ground. Because I know my initial was 30 seconds, phase 1. Phase 2 was 122 seconds. I need to find time for phase 3. Well, let's take a look. I don't know the final. I don't really need it for this problem, the instant before it hits the ground. First equation, v final equals v initial plus acceleration times time. Well, I don't know v final. Second one, y final equals y initial plus v initial times time plus 1/2 at squared. Well, y final in this case is 0, y initial 54,800 meters, so I know that. My initial velocity is 0, so that term ends up being 0. So I can use that equation, and that's really delta t. So what I have is y final equals y initial plus v initial times time plus 1/2, and I'm going to say t final minus t initial squared. So really, or we could just call that t. Either one works out. So y final is 0, this goes to 0. V initial is 0, that term goes to 0. So now let's solve this, or let's just solve it for t. So what I end up having here, and that should be 1/2 a, sorry, 1/2 at squared. Well, what I end up is minus y initial, okay, equals 1/2 at squared. I'm going to solve for t. T then is equal to minus y initial times 2 all divided by a, and take the square root there. So t is going to be equal to the square root of minus 54,800 meters times 2 all divided by a minus 9.8 meters per second squared, and then take the square root of all of that. Okay, now I need to go back for just a second here because I failed to do something. This actually, if we plug it in, I grab, is about 91.8 or 92 seconds. Okay, if you do that, if you do this equation, it ends up being 900 divided by 9.8, or minus 900 meters per second squared meters per second divided by 9.8. You get about 91.8 for your time in phase 2. And then we can figure this one out here for phase 3. This then equals about 105.7 seconds. Now to get my total time, I'm going to have T1 30 seconds, for phase 1 30 seconds, phase 2 about 91.8 seconds, phase 3 105.7 seconds, and when you add all those together, then you're going to get the total, which is roughly 227.5 seconds. Whew. So lots of work to come up with my maximum height, 54,800 meters, my total time, 227.5 seconds. And the big thing in this is just understanding, looking at the problem and taking it piece by piece. Phase 1, the rocket is firing. Phase 2, the rocket engine stopped, but it's still rising and hits a maximum height. Phase 3, it falls back to the ground, and we just take that piece by piece by piece and looking at each one of them to come up with our final answer to finish the problem.